Hi, today we're going to look at exercises which imply elastic collisions. So we know that when there's a collision and it's a closed system, so no external forces are applied, the momentum is conserved. So the momentum after equals the momentum before. And in an elastic collision, apart from being a closed system with no external forces applied, where the momentum is conserved, the energy is conserved. So if we consider this kinetic energy, the initial kinetic energy has to be the same as the final kinetic energy. So there's something very important in this sort of exercises. We're going to look at, for example, the sort of exercise where there's an object that's going to collide with another object. Let's call this one m1 and m2 with velocities, initial velocities u1 and e2, and they will end up moving with a final velocity h1 of v1 and v2. Okay, so let's look at what happens here. So if we apply the momentum is conserved, we know that m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So here I'm applying that the momentum, which is the mass times the velocity of each object, initially equals to the momentum, equals the final momentum of each object. Okay? So from this equation, we can obtain, and we'll see why we're going to need it, that m1 u1 minus v1 equals m2 v2 minus e2, where I've moved the m1 v1 to the left and I've factorized the m1, and I've moved the m2 u2 to the right and I've factorized the m2. We'll see why we need it later. So if we apply that it's an elastic condition, so the kinetic energy is conserved, if we calculate the kinetic energy on each object, so you have m1 u2 u1 squared plus a half m2 u2 squared equals half m1 v1 squared plus a half m2 v2 squared. Okay, so we can start by removing cancelling the halves, because if we factorize a half on each side of the equation, well, this can be removed, so we can factorize that. And then we can do this. We can do m1 u1 squared minus v1 squared, and I'm doing the same thing as I did before, equals m2 v2 squared minus v2 squared. Okay, but this is a perfect squared. u1 squared minus v1 squared is a perfect squared. If you remember, a plus b times a minus b equals a squared minus b squared. Okay, so I'm going to apply that here, and I'm going to rewrite this equation as m1 u1 plus v1 times u1 minus v1, and that equals to m2, and I'll do the same thing here, v2 minus u2, v2 plus u2. Okay, but remember, m1 from the first equation, m1 u1, so this part over here, which is this part over here, equals m2 v2 u2, okay, which is m2 v2 u2. Okay, so what I'm going to do is if they are equal, they can be cancelled out. So this one and this one, I'll cancel it out, and this one and this one can be cancelled out. So we obtain u1 plus v1 equals v2 plus u2. Okay, so again, I've used both equations and I've rewritten them correctly, factorizing the m's and doing each equation, and I see that m1 u1 minus v1 equals m2 v2 minus u2, so I can, they're at both sides of the equation, so I can cancel them out if they're equal and obtain this. So in the end, I have that u1 plus V1 equals V2 plus U2. Okay. So what I'm going to do now, I'm going to move the initial velocity to the other side. So U1 minus U2 equals V2 minus V1. And if we rewrite this correctly, U1 minus U2 equals, and I'm going to write the ones first, so I'm going to write minus V1 minus V2. Okay. So if we call U1 minus U2 the relative velocity of object 1 versus object 2, so the initial relative velocity of 1 versus 2, well, that's to be equal to the initial relative velocity, the final relative velocity of, this is the final relative velocity of 1 versus 2, but with a minus there. Okay. So when we have elastic collisions, the important part to remember, and we can go directly to this final equation, is that the initial velocities, the initial relative velocities, has to be the same, has to be opposite and the same in value as the final relative velocities, just because the energy is conserved. So in the next video, we'll do an exercise about this where you can see the numbers.